going to talk about symmetry in force entanglement from projective non-invertible symmetry. Okay, so please, Hotat.
Great, great. Thanks for the introductions, and also thanks to the organizer for the invitations. I had a very fond memory visiting ICTP almost 8 years ago for the Bootstrap summer school. But unfortunately, this time because of my visa issue, I cannot make it in person. And thanks to the organizer for giving me this opportunity to speak remotely. So today I'll tell you something about symmetry in force entanglement from projective non-invertible symmetry. And this is based on the work done in collaborations with these two gentlemen from MIT, Sao and Omer. So Sao is a rising fifth-year grad student, and Omer is a rising third-year postdoc. So both of them are applying this year. Pay attention to them, and I highly recommend them. Okay, and let me now begin with an introduction. And I understand that the audience is very mixed with experts from very different backgrounds. So my plan is that I will give a relatively long and pedagogical introductions, covering some basics about SPTs and Atoll anomalies. But still, some of the things I'm presenting might be useful for even the experts. And after that, I'll talk about the consequence of projective non-invertible symmetry. So let me begin with the unifying questions that exist in both high energy and condensed matter physics. That is, given the microscopic UV systems, we would like to determine its emergent macroscopic IR behaviors. And depending on your backgrounds, these systems might be defined by some quantum field theories or some lattice models or some many-body systems. But to answer these questions, in most cases, are extremely hard because of strong couplings. But fortunately, because symmetry actually gave us a universal tool to tackle these problems. And in particular, its utility comes in two ways. One is that it provides us with organizing principles for distinct infrared behaviors through the Landau paradigms. And they also give us different constraints on the infrared physics through, for example, Atoll anomalies or Lifshitz-Madness theorems. I'm going to expand about what I mean by this in the coming slides. So what are the possible IR possibilities? So we can organize them, roughly speaking, in terms of the spectrums in their gaps. So we can divide the IR possibilities into gapless case and gap case. And gapless case are relatively easy to understand in the sense that they are basically some critical phenomena or gapless phases. And often the case they are described by conformal field theories, but there are also other possibilities. And for gap cases, in 1+1 dimensions, we can organize different possibilities according to how the symmetries are behave. So in particular, there's phases where symmetries are spontaneously broken, and there are also phases where symmetry is preserved. But if we go up in higher dimensions, there's also a possibility of topological orders, which are described by some topological quantum field theories. And in dimension greater than 1+1 dimensions, then a continuous symmetry can also be spontaneously broken and lead to ghost bosons. So these are sort of the rough pictures of what are the possible IR possibilities. So let me in particular say a little bit more about symmetric phases, in particular what's called the SPT phases. So this will be useful for later discussions. So what are SPT phases? So SPT phases, in short, they stand for symmetry protected topological phases. So in short, that means they are symmetric gap phases with a unique gap with a unique ground state on every closed manifold. So in some sense, they are the most trivial phases, but still there are many interesting phenomena related to them. So for example, distinct SPT phases cannot be continuously connected by symmetry preserving path. And there are some characteristics of SPT phases. So one properties is that their ground states are short range entangled. When I say short range entangled, what I mean by that is that the ground states are connected to the trivial product states by finite depth quantum circuits. So we can just start with the product states and then just add gates in finite layers. Then we can prepare the ground states for this SPT phases. And this SPT phases are also characterized by the response to background gauge fields. In particular, this response means that it's captured by partition functions, which is just simply a phase. And the phase can have a non-trivial dependence on the background gauge fields. And because this is a phase, every phase has an inverse. So that's why it's called invertible theories in mathematical terms. So this SPT phases also exhibit interesting physics on the boundaries and interfaces through a phenomenon called anomaly inflow. That there's non-trivial anomalies that is inflow from the bulk of SPT phases to the boundaries or interfaces of SPT phases. So let me do an example of SPT phases, which might be not the conventional ones that people talk about. So this is what's called Z2 weak SPT. So the setup is that we consider a 1+1 dimensional periodic spin chain with a qubit on each side. So this is basically a two-level systems at each side. Then we can consider the following two Hamiltonians. One of them is basically given by minus sum over x on every side. The other is given by plus sum over x on every side. So if we stare at these two Hamiltonians, both of them have the same Z2 symmetries, which is given by the product of x. So we'll denote that by U. And both of them has lattice translation symmetries. And it's very easy to solve the ground states. So the ground state is simply a product state. So it's also a unique and gapped. So it has a unique gap, short range entangled ground states. And in that sense, these two Hamiltonians are both what's called Z2 weak SPT. So Z2 weak SPTs are SPTs that enjoys both the Z2 symmetries, which is the symmetry given by product of x, and lattice translations. So the questions we would like to ask is that are these two Hamiltonians that I wrote down, that probably the most trivial Hamiltonians that we can ever written down, are they in same Z2 weak SPT phases or different Z2 weak SPT phases? So we can answer that by checking the response to the symmetry defects. So in particular, we'll insert the symmetry defect for the Z2 symmetries. So what are symmetry defects? So symmetry defects is a concept that I will use extensively later. So they are local modifications of the Hamiltonians that are created by truncated symmetry operators. So our symmetry operators are defined on the whole systems given by product of x. We just truncate it, okay? So we truncate it so that we have a product of x acting from a side to infinite distance. And so we can sandwich our Hamiltonians between these truncated operators. Then this will create a defect sitting at the end of the truncated operators. And this defect will modify the Hamiltonians into defect Hamiltonians. So one important thing to is that once I have a defect, then translation symmetries will be modified. And the new translation symmetries is given by x acting at this side times t. So let me explain why the translation symmetries are modified. So the reason is the following. So let's try to first do a translations. So if we do a translations, then we'll move all the truncated operators to the right-hand side. So we move the defect from one length to the other length. So we obtain the different Hamiltonians. But we can remove this, we can undo this transformations by applying x at this side. And as a result, we recover the same Hamiltonians. So this means that whenever we have a symmetry defect inserted, translation symmetries are modified. And this actually has a consequence. So one consequence of this is that if we study systems with on periodic chains with a symmetry defect inserted, then this will twist. What it does is that it's basically twisting the boundary conditions. So when we go around the system sites, which amounts to applying translations L times, we amounts to applying symmetry transformation once. So that means that the operators, when you go around the system once, it will be transformed by the operator, by the symmetry operator U. And that's what I mean by twisted boundary conditions. So now, using this symmetry defects, we can now go back to answer these questions. that are these two Hamiltonians that I wrote down before, same Z2 weak SPTs or different Z2 weak SPTs. So first to notice is that my Hamiltonians are not modified if I insert a symmetry defect, because my truncated symmetry operators is just given by product of X, and my Hamiltonians are proportional to sum of X. So that commutes with the truncated operators. So the Hamiltonians are not modified. And as a result, the ground state remains unchanged. So the ground state is still given by just product of a product states, which is either product of plus states or product of minus states. Both of them are eigenstates of X. But now notice that because I insert a symmetry defect, translation symmetry operators need to be modified. So this is my new translation symmetry operators. And this actually have a consequence. So its consequence is that now we can ask, how does the translation symmetries act on the ground states? So so let's first consider a case when the system size is even. So in that case, if we act, the ground states that we wrote down are both symmetric under U and T. On the other hand, if now we insert a Z2 symmetry defect, we modify the translation operators. So now there's this additional X sitting in the definition of the translation operators. And this X can distinguish the two ground states. So that means that if we insert a symmetry defect, the translation symmetries now act differently on the ground states of Hamiltonian H plus and a ground state for the Hamiltonian H minus. And in particular, this means that now in Hamiltonian H minus, with the Z2 symmetry defect inserted, translations will act with a minus sign. So that means that the Z2 symmetry defects actually carry a momentum, a pi momentums in H minus. So, and we know that momentums are charges under translations. So that means that Z2 symmetry defects actually carry charges under translation symmetries. And there's we can also ask what happens to the systems when we put it on when we change the system size from even number to odd numbers. So if we change the system size from even number to odd numbers, or the symmetry actions of the Z2 symmetry actually will change. And in particular, on odd length periodic chain, the Z2 symmetries acts on the ground states of H minus with a minus sign. But you can ask, what does this mean? So we can interpret this odd L, this minus sign for the odd L periodic chain as the following. So we can interpret that the odd L periodic chains as an even L periodic chains with a translation defect inserted. So the reason why I say that this is amounts to inserting a translation defect is the following. So remember that when we insert a symmetry defect, then it will modify the translation algebras. So we will have T to the power L equals to U. But in this case, the U for translation symmetry is basically T. So this simply means that we are modifying the translation algebra to T from T to the power L equals to 1 to T to the power L minus 1 equals to 1. So that means that the system size is actually shrink by 1 unit. And we interpret the shrinking of system size as an insertion of translation defects. So now if we compare the odd L versus even L, then it amounts to inserting a translation defect. And then this minus signs can be interpreted as the translation defect carries a Z2 symmetry charge if the Hamiltonian is in the H minus Hamiltonians. And these two behaviors of symmetry defects, that the fact that this symmetry defects carry different symmetry charges is a signature that H minus is in a non-trivial SPT, Z2 weak SPT, compared to the H plus state. So in particular, one can actually write down the response of this Z2 weak SPTs. So for the H plus, the partition function is simply a trivial partition functions. But for H minus, the partition functions is given by e to the power I times pi integral of A cup EX. So this A can be thought of as the background gauge fields for the Z2 symmetries. And this EX is the tetra field. And this tetra fields can be thought of as sort of the background gauge fields for translation symmetries. So this is a response for the Z2 weak SPTs, which distinguish the H minus Hamiltonians from H plus Hamiltonian. So now, after I explained to you what are these SPT phases, now I would like to discuss how we can distinguish different infrared behaviors according to the entanglement patterns of ground state wave functions. So as I said that the SPT phases, the ground states are given by what's called short-range entangled states, meaning that the ground states are created by product states by acting some finite depth unitaries, finite depth quantum circuits on product states. But it turns out that only the SPT phases are the only states whose ground states are short-range entangled. And all the other phases all the other infrared possibilities that I written here, including both gaplets, symmetry breakings, and topological orders, their symmetric ground states are all given by some long-range entangled states. When I say long-range entangled, that means that if I want to prepare the states from product states, I need to act not a finite depth quantum circuit. I need to act quantum circuits with a depth that is at least the system size. Okay, so this tells us that by looking at the entanglements of the ground states, we can already distinguish SPT phases from the other infrared possibilities, such as symmetry breakings and gaplet phases or topological orders. So this is one main message of the slides, that the infrared physics can be organized by the entanglement properties of the ground state wave function. So now I would like to turn to discuss the 12 anomalies. So in particular, notice that when we have a symmetry can have a 12 anomalies. So a 12 anomalies is basically an abstractions to symmetry protected topological phases. So if you look at this, this actually also has the consequences to the ground state entanglement. So if a symmetry has a 12 anomalies, then this tells us that the theory cannot admit a unique gap ground states without topological orders. So if the theory has a unique gap ground state without topological orders, then this is basically SPT phases. But by definitions, a 12 anomalies exclude SPT phases. And also, a 12 anomalies, there's a trivial corollary from this diagram, is that a 12 anomalies also exclude ground states that are short-range entangled. So it forces that symmetric ground state has to be or must be long-range entangled. So this is the first examples of how a symmetry can give us a non-trivial entanglement constraints on the entanglements of ground state wave functions. So let me do an examples of a 12 anomalies. So this is what's called Lifshitz-Mattis anomalies. So again, we can consider the same setup I discussed before. Let's consider a 1 plus 1D spin chain with a unitary symmetries associated with some group G. So the simplest 12 anomalies the symmetries can have arises if the symmetries act projectively, act in the local Hilbert space in a projective way. So that means that if I look at the symmetry actions of the symmetries at a site, then the symmetry acts, the Hilbert space at that site transform as a projective representations under that symmetries. So when in all these discussions, when I discuss symmetries, I always consider symmetries that commutes with translations, meaning that the symmetries is basically a product of same kind of operators acting on every site. So in particular, a symmetry operators labeled by a group element G is given by product of UG acting on every site. Okay. And this UG operators at every site can have non-trivial projectivities, which are characterized by this phase, which depends on both G and H. And this thing is usually given by a second group cohomology. Once the Toph anomalies acts projectively on a local Hilbert space, then this Toph anomaly, then the symmetries has a Lipschitz-Mattis anomalies. So a Lipschitz-Mattis anomalies is basically a mixed anomaly between these symmetries and lattice translation. So we can detect this Lipschitz-Mattis anomalies through the following method. So let's consider a translation defect. So which basically means that we just put the systems on a periodic chain, and then we keep changing the system size L. And then we compare what happens to the symmetry algebras. So what we find is that because this symmetry operators, because this local unit of the symmetry operators, UG and UH, they form some projective representations. Then as a result, the actual symmetry operators, which is given by product of UG and UH, they would form some non-trivial projective algebra. But this projective algebra is controlled by the same phase that appears in the local projectivities. But then but this phase will depend on L. So in particular, if we change L by 1 unit, then this will change this phase by 1 unit of exponential I phi. So this means that translation defect carries projective representations under a symmetry G. And similarly, we can now insert a symmetry defects for the symmetry G. So for example, let's insert a symmetry defect for UG. And as I explained already before, that once we insert this defect, then this will modify the translations to be translations which are multiplied by UG. Okay. And there's an extra consequence that happens if this group is non-abelian. That is, this will break the G symmetry down to the centralizer of this group element, little g. And so we will just, so if we study the defect, the modified defect Hamiltonians of UG, the residual symmetry includes a modified translations and the centralizer symmetries. And this two symmetries can form a projective algebras. And again, the projectivity is given by controlled by the same phase that appears in the local projectivity. And the reason why we have this projectivity is because now translation is modified by multiplying a local UG. And this local UG can have non-trivial phases if we commute it past, if we study its commutations with some UH, with H coming from the centralizers, okay? So this two projective algebras are a way to detect basically a signal that there's a Lipschitz-Mattis anomalies in the systems. So this is a sort of a signal that there's some non-trivial anomalies in the systems. And for an expert, one can understand this Lipschitz-Mattis anomalies using a one-dimension higher SPTs through anomaly inflow. And this one-dimension higher SPT is a 2 plus 1-dimensional weak SPTs, which is SPTs protected by translations along in the same directions as parallel to spin chains, and also the G symmetries. And in particular, this is the SPT actions, which is determined by the local projectivities and multiply with the tetrafield. Okay, so this is the SPT actions that characterizes the Lipschitz-Mattis anomalies. Okay, so I keep telling you that there's this Lipschitz-Mattis anomalies, and I told you that how we can detect them and characterize them. But then what are the consequences of this Lipschitz-Mattis anomalies? So the Lipschitz-Mattis anomalies, a direct consequence of that is what's called a Lipschitz-Mattis theorems. That this Lipschitz-Mattis anomaly forbids a unique gapped ground states. Namely, the existence of this Lipschitz-Mattis anomalies tells us that the theory cannot flow to SPT phases. And this Lipschitz-Mattis anomalies arises from the local projectivities of the symmetries. So let's do an examples of symmetries that exhibit this kind of Lipschitz-Mattis anomalies. So which is given by projective Z2 times Z2 symmetries acting on the same 1 + 1 dimensional spin chains, but now in this case of a qubit. And so we have two symmetries. One of them we denote by ux, the other we denote by uz. And ux is built from product of x, and uz is built from product of z. Okay, but notice that x and z, they are Pauli matrices, and they don't commute, and their non-commutativity is up to a minus sign. So that means that the z2 times z2 symmetry actually, if they act linearly on some representations, then this two symmetries supposed to commute. But now, because of this minus signs, then this tells us that this z2 symmetries cannot act linearly on the local Hilbert space. They in fact the local Hilbert space form a projective representations under this z2 times z2 symmetries. So now one can ask, what is a consequence of this local projectivity? So one consequence is that, as we said before, the translation defect now carries z2 times z2 projective representations. And in particular, if we study the systems on periodic spin chains of odd length L, then the symmetry ux and uz will not commute. And their non-commutativity is given by a minus sign. And this has a consequence that the ground state must be twofold degenerate. And similarly, if we now insert the ux defect, this will modify translations to translations where the translation is multiplied by by x acting on site 1. Then this modified translations and uz will form projective algebras with again a minus sign. And this tells us that there must be twofold ground state degeneracies in the ux defect Hilbert space. And let me compare this projective algebras with what happens if we study symmetry defect in SPT phases. So if we study symmetry defect in SPT phases, we see that those ground states can carry the non-trivial charges under the other symmetries, but they are always transformed as linear representations under the other symmetries, in contrast to projective representations. So this is sort of a quick way to see that why Lipschitz lattice anomalies or projective symmetries are incompatible with SPT phases. And so let me give you more rigorous proof, sort of arguments of why this Lipschitz lattice anomaly or projective symmetries exclude SPT phases. So let's assume that, let's prove it by contradictions. So let's assume that the theory has a unique gap ground states. Then one can show that the defect Hilbert space for unitary symmetries also have a unique gap ground states. But then in both cases, we have shown that for both translation defect and UX defects, there are twofold ground state degeneracies. So this contradicts with the assumptions that we made. Hence, our assumption is incorrect. So this tells us that Lipschitz lattice anomaly actually forbids a unique gap ground state. So in particular, in this case of a Z2 times Z2, a projective Z2 times Z2 symmetries, we have the following Lipschitz lattice theorems. That is, any translation invariant Hamiltonian with a projective Z2 times Z2 symmetry cannot have a unique gap ground state. And a corollary of that is that its symmetric ground states must be long-range entangled. And an example of Hamiltonians that respect this projective Z2 times Z2 symmetries and also respect translation symmetries is what's called the XY models. So this is a Hamiltonian that includes two kinds of terms. One is the terms given by product of X at neighboring sites, and the other is the product of Z at neighboring sites. So usually it's supposed to be product of Y, but I decided to use the product of Z here so that it will be useful for later generalizations. So this Hamiltonian, if we study its phase diagrams by tuning gammas, its phase diagrams is given by something like this. So so we can tune gamma from -1 to 1. So from -1 to 0, the theory is in a spontaneous symmetry breaking phase. Which is in a phase where it's called a nu X phase. So let's consider the extreme case where gamma equals to -1. Then in that case, we don't have this term, and we only have this terms. So it's easy to see that the Hamiltonian has a twofold degeneracies, and the symmetric ground states is basically given by sort of a GHZ states, but now it's made of a states that is given by plus minus plus minus plus another states which is given by minus plus minus plus, where all of the spins are flipped. And if we cramp gamma up to be in the regime where it's between 0 and +1, then this is in what's called new Z phase. So in this phase, the theory again has a spontaneous symmetry breakings, which has twofold degeneracies. And the symmetric ground states is again sort of a GHZ states, which also exhibit long-range entanglement. So ground states in both this phase and this phase has long-range entanglement. And in both cases, we see that there are degenerate, even though the systems are gapped, but then you have degenerate ground states. So both of them are consistent with the Lipschitz-Mattis theorems. And in the middle case, the theory actually goes through a phase transition, so critical points, where the theory is described by the bosonizations of the Dirac fermions. So this theory is gapless, is described by a conformal field theory, and this is again compatible with the Lipschitz-Mattis theorem. And these ground states are also long-range entangled. Okay, so this basically concludes my introductions and sort of a review of materials. Now I would like to get into the meat of today's talk. That is what happens. I would like to ask the questions, what happens if we now have a projective non-invertible symmetries? So in previous example, we have seen that once we have a projective unitary symmetries, then this lead to Lipschitz-Mattis anomalies, and then this gives us a constraints on the Hamiltonians that respect those kind of symmetries, telling us that those Hamiltonians cannot flow to SPT phase. But now we want to ask what happens if we have a projective non-invertible symmetries. So this is the questions we would like to answer. So to answer this, let's get into some concrete setup. So the setup I'm considering is again in 1+1 dimensions, and it's again a spin chain. But now at every side, so we put, instead of a qubit, we put some a generalization of a qubit called G-qubit. So G-qubit is a kind of a systems based on group G. So G-qubit is a systems with dimensions given by the cardinality of the group G, given by the size of the group G. And the Hilbert space is basically spanned by a bunch of states labeled by the group elements of G. And on this Hilbert space, we can define generalizations of Pauli matrices. So there's a generalization of the Pauli X operators, which has two types, because now our group is non-abelian, so it actually matters. So these Pauli operators are labeled by a group element G. And when they act on the state H, then they can act on that by multiplying H by G, or multiplying H by G inverse from the other side. And because the group in general are non-abelian, so these operators and this operator in general are different. So they are the same only if this G are in the center of the group. So in that case, GH and H G inverse. Oh, actually, so this thing is the inverse of these things. If G is in the center of the group. So in that case, GH is the same as HG. There's also generalizations of the Pauli Z operators, so which is a little bit more complicated. So this operator is labeled by the representations of the group now. So gamma is given by is an E-rep of the group G, and this operators has additional labels given by alpha and beta. So alpha and beta are indices that run from 1 to the dimensions of the representations. So when I act this generalized Pauli Z operators on the state G, then I get the matrix elements of the representations of the group element G in gamma. Okay, so this is the generalization of the Pauli Z operators. So as a sanity check, if we take this group G to be Z2, which has has two elements, the trivial elements and the non-trivial elements. Then the G-qubit systems basically reduces to the standard qubits. So this is a two-level systems, and the Pauli matrix is given by basically X the X operator associated to non-trivial elements. And as Z2 symmetries, there are two non-trivial ERAPs. One is the trivial ERAPs, and the other is the sign ERAPs. So the sign ERAPs now acts on the sign ERAPs now acts as Pauli Z operators. I think this is a typo. There's a typo here. So this Z operators associated with sign representations it reduces to the Pauli Z operators. Okay, so this is a generalizations of qubits to G-qubit. So now using this, we can build a generalizations of the XY model. So this is a generalization of the XY models. So it consists of two kind of terms. One is given by product of X terms, and the other is given by product of Z terms. So don't worry too much about the details. This is just a Hamiltonians, just to show you the Hamiltonians. The things that we care the most is actually the symmetries of this Hamiltonian. So what are the symmetry of this Hamiltonians? So there's obvious symmetries, which is translations. The whole Hamiltonians is invariant under translation. There's another symmetries which is given by the center of the group G. So this is a unitary symmetries where the symmetry operators is given by product of X to the power is given by product of X with group elements Z, where this group elements is the center element of this group. There's again a typo. There's some this should be the inverse of these things. So one can check that this is a symmetry of this Hamiltonians because X associated with the centers commutes with all of this X, and this commutes with when we commute this past this, we create a phase, and when we commute this past this, we create another phase, but these two phases cancel out. So this is the symmetry of this Hamiltonians. And in particular, if we take two such symmetry operators labeled by Z1 and Z2, if we fuse them in sense of multiplying them, then we just obtain the symmetry operators labeled by Z1 times Z2. So this operators obey group fusions, which is governed by the group multiplications of this center group G. There's a more interesting symmetries hidden in these systems. So this symmetries is given by it's a kind of a weird kind of operators. So this is operators that's given by product of Z. So we multiply all of the Z, but now remember that all the Z operators has like additional indices. So what we want is that we want to multiply all of the Z's, and then we want the index of one side to be the same as the index, the beta index of one side to be the same as the alpha index of the next side. So this index, and then we sum over those indices. So in that sense, these are like matrix multiplications. So we are multiplying a bunch of matrices, and then eventually we take the trace. Okay. So this symmetry operators are similar to how we label this Z operators. They are labeled by the ERAPs of this group G. And then if we try to fuse these two operators, then this is just like fusing two representations. So if we fuse two representations, we get some additional representations. We can get some representation. We can decompose that into ERAPs. And then when we decompose it into ERAPs, there could be non-trivial multiplicities. And this is exactly this multiplicity, this number that appears here. So in other words, this symmetry operators simply, they are labeled by the ERAPs of G. And then if we fuse them, they fuse like ERAPs of G. So that's why they are called RAP-G symmetries. So I want to make a quick comment about the property of these symmetries. So if this ERAPs is one-dimensional, then this operators is actually unitary and invariable. And in particular, if I multiply one-dimensional ERAPs to any other ERAPs, it can only give us a single ERAPs. Okay, So there's only a unique possibilities that come out from the other side. So in that sense, this operator is invariable in the sense that if we multiply these operators to these operators, we get single operators on the other side. And if this operator always has inverse because it's unitary. We can just multiply these operators to the operators associated with a complex, the conjugated representations, and then they will just give us the identity operators. On the other hand, these operators will behave extremely differently if we take the dimension of the representations to be greater than 1. So this happens if the group is non-abelian. So in that case, this symmetry operators becomes non-invariable. So they are non-invariable in several sense. So they're non-invariable in the most intuitive sense that there exists some states that are annihilated by these operators. So because there are states that are annihilated by these operators, so that means that there are states carries eigenvalues. There are states which has 0 eigenvalues. So as a result, this operator is not invariable. And this operator is also non-invariable in the sense that if we multiply these operators with its complex conjugations, then we can get multiple operators living on the right-hand side. And that's another sense of non-invariability. So a way to think about the symmetry, sort of a useful way to think about the symmetry operators is through what's called the matrix products operators. So this is similar to what I described to you before, that we can represent this operator Z by the following diagrams. So it's like sort of a tensor with multiple legs coming out. So the black legs are the physical qubits, and then the gray legs are the virtual qubits. And then we basically, when we want to build a symmetry operators, what we do is that we basically just take a bunch of this matrix valued operators labeled by alpha and betas. We just multiply them. And then we contract their virtual index, and then eventually take a trace. Then this defines for us the symmetry operators for this RAP-G symmetries. So it turns out that if we want to study non-invariable symmetry on lattice, this so-called matrix product operators, which are given by basically product of matrix operators, are a natural way to formulate this non-invariable symmetries. Okay, so now let's review what are the symmetries again in these models. So the symmetry in these models include symmetries given by the center of the group G, which is a unitary symmetries, and the non-invariable symmetries given by RAP-G. Okay, and if we look at the symmetries, they are basically generalizations of the projective Z2 times Z2 symmetry we studied before. One of them is generated by product of Z, and the other is generated by product of X. So similarly, here's generated by product of X, and the other is generated by product of Z. And if we take this group G to be Z2, then we just reduce this to the same projective Z2 times Z2 symmetries that we have seen already before in a cubic in a spin chain of qubits. So now, if we now we can ask what happens if to the building blocks of the symmetries. So the ZG symmetry is basically built by this X Z operators. On the other hand, this RAP-G symmetries are built by those matrix operators that is given by Z gamma alpha betas. And one can check that these two operators actually don't commute, just similar to the fact that poly X and poly Z don't commute. And their non-commutativity is controlled by a phase. So this phase is the phase that appears in the representations of center elements in this representations. So a center element, if we look at these representations, is always proportional to identity because it commutes with every element in the group. So by Schur's lemma, it will just be proportional to identity operators. And then, but however, there can be a phase that appears in the front, and that phase is a phase that appears here that controls the projectivity. So now we can ask, how does this projectivity affect the various symmetry algebras in the presence of defects? So first, let's consider the case when there's a translation defect. So that means that we just put the systems on some periodic chain, and then we change the system size. So if we change the system size, what we find is that the rep G symmetries and the center G symmetries, they don't commute, and their non-commutivity is given by a phase. That phase has a non-trivial L dependence. So this L dependence means that translation defects, in some sense, are carrying some kind of projective representations. And similarly, if we now insert the defect for UZ, which is the defect for the center unitary symmetries, then what it does is that it will modify the translation symmetries, and this modified translation symmetry has an additional X multiplying the translations. This additional X and the representations and this rep G symmetries, they won't commute, and their non-commutivity is given by a phase. And this is the same phase that appears in the local projectivity. And more interestingly, we can also insert the symmetry defect for the non-invertible symmetries. So to create the symmetry defect for non-invertible symmetries, what we want to do is that we want to truncate the symmetry operators. But to truncate the symmetry operators, what we need to do is to use the matrix product operators representations of these truncated operators. So what happens is that we will truncate the symmetry operators by cutting the virtual links open, but then this virtual links has to go somewhere. So what happens is that this virtual links, which carries some virtual Hilbert space, now actually becomes an actual Hilbert space that becomes part of the physical systems. So what happens is that we can fit in the Hamiltonians, and then it will feed out a Hamiltonians on a larger Hilbert space. So we are enlarging the Hilbert space by a d-dimensional Hilbert space. And this d dimensions is basically the dimensions of the representations of this representation gamma. And we can interpret this additional Hilbert space as the internal Hilbert space of the defect. So now on this, if we look at the modified Hamiltonians, what we will see is that the translations is again modified. And this modification is very simple. It's basically just the translations that acts on the systems, and together with Z operators that now acts on both the qubits at site 1, the G qubit at site 1, and then the virtual Hilbert space. And this modified translations again form some projective algebras with the center symmetries. So in conclusions, we have seen that this ZG and rep-G symmetries, they act in the they act on a local Hilbert space in a projective way, and as a result, they lead to some non-trivial projective algebras in the defect Hilbert space. And the questions we would like to ask now is that whether there's actually an anomaly. So anomaly or no anomaly, and that's the question. So does the projective non-invertible symmetry lead to an LSM anomalies? So that's the question we would like to answer. So the answer to this question is actually surprisingly not always the case. So this is different from the projective invertible symmetries. So in the case of projective invertible symmetries, whenever we have a local projectivities, then we always have a Lipschitz-Mattis anomalies. But in this case, there's actually a counterexamples one can construct. It actually took us a while to construct these counterexamples. But the upshot of this counterexample is that one can actually find weak SPT phases, which is a SPT phases that has both translation symmetries and the center symmetries and the rep-G symmetries. And this SPT phases has a unique ground states on every manifold. And the Hamiltonians, and so what we did is what we did is that we only constructed for the group G when it's equals to D8, which is given by a dihedral group of order 8. So in this case, this is the Hamiltonians that have a unique ground states, which describe non-invertible weak SPT. So this Hamiltonians turns out has the Z2 symmetries, which is the center symmetries. And the Z2 centers of the dihedral group is given, so the dihedral group is generated by two generators, R and S. So the center is given, S has order 4 and R has order 2. The center is given by S squared. So S squared, if you square it, if you add 4, which equals to 1 by this equivalence relations. So that's why this generates a Z2 symmetries. And on top of that, there's also RAP-DA symmetries. So RAP-DA symmetries are symmetry operators labeled by the representations of the dihedral groups. So dihedral groups in total have 5 representations. So 4 of them are one-dimensional ERAPs, including the trivial ERAPs. And then one of them is a two-dimensional ERAPs. So what happens is that if we look at the projective algebras, what we have seen is that the Z2 symmetries actually has trivial projectivities with all of the one-dimensional ERAPs. However, it has a non-trivial projectivity with the two-dimensional ERAPs. And this projectivity is reflected by this algebras, which has a phase that depends on the -1 to the L. Okay? So, in this case, we see that there's actually a counterexamples that even though there's a non-trivial projective algebras that we can construct similar to the projective invertible symmetry algebras that we already seen before, we actually can find SPTs that respect these symmetries. So that tells us that the symmetries cannot have anomalies. So this means that there must be some loopholes in the arguments that we had for unitary symmetries if we want to apply it to non-invertible symmetries. So what are these loopholes? So let's first consider the arguments using translation defect. So if we have a translation defect, then we have the following projective algebras where a RAP-G symmetries and the ZG center symmetries don't commute, and their non-commutativity is given by a phase that depends on L. So let's first consider a case when this representation is one-dimensional. If this representation is one-dimensional, then the operators is unitary. So in this case, one can actually prove that this algebras implies that this algebras, if this phase is non-trivial, implies that there's a Lifshitz-Mattis anomalies that forbid a unique gap ground states, or in other words, exclude SPT phases. So to prove it, we can do it by, again, a proof by contradictions. So let us first assume that there's a ground state that is unique and gapped. So because this is unique and gapped, so this ground state must be symmetric under all the symmetries. So this is symmetric under the ZG symmetries and also the RAP-G symmetries. And because both symmetries are unitaries, so the ground states can, the eigenvalue of the ground states are at most some phases. So now if we take the system size to be an L such that this phase is non-trivial, then we can derive the following contradictions. So we can evaluate R gamma and UZ on the ground states. If we evaluate this ways, then we will read off the two eigenvalues. On the other hand, what we can do is that we can swap them. So we can swap them using the projective algebras, then there's a non-trivial phase that comes out. And now, because of this non-trivial phase, so after we get this non-trivial phase, we can again evaluate this on the ground states. Then we get, again, the two eigenvalues. So what we have seen is that we get a phase here and a phase here, but these two phases don't agree with each other because we pick L such that this phase is non-trivial. So hence, we derive the contradictions that the ground state cannot be unique. There must be some non-trivial degeneracy in the ground state wave function, in the ground state subspace. So hence, this proved the Lifshitz-Mattis anomalies. So now let's consider a case when the dimension of this representation is greater than 1. So in that case, the operators that we consider is not unitary or invertible anymore. They're actually non-invertible operators. And if this is a non-invertible operators, then it opens up the possibility that these operators can annihilate the ground states. And in fact, we can run the same argument as before, but now because this operators can annihilate the ground states, we can simply satisfy it, we can resolve these contradictions by demanding that the symmetry operators or gammas actually annihilate the ground states. So an SPD phase can actually exist or can be compatible with this projective algebras if this non-invertible symmetries annihilate the ground states for every L such that this phase is not trivial. So this is what happens for translation defects. We can try to prove an LSM theorem through another route. So that is through the symmetry defect for the Z2 for the center ZG symmetries. So if we insert the symmetry defects, this is algebra that we obtained. So there's a non-trivial algebras between translations, the modified translations, and the non-invertible symmetries. So let's again first consider a case when the dimension of the representations is one-dimensional. In that case, the operator is unitary. So in that case, one can again follow the same arguments, show that there's a non-trivial Lifshitz-Mattis anomalies. And the idea is as follows, that if we assume there's SPD phases, then this implies that there must be unique ground states in the defect hubris space of this UZ symmetry defect. But however, by running the same arguments, we can show that there must be non-trivial degeneracies in the UZ defect hubris space if this phase is non-trivial, and hence we derive a contradictions. But now, if we take the dimension of the representations to be greater than 1, then this opens up the possibility that this operator is non-invariable, and so the SPD in principle can exist if this operator is actually annihilate the ground state for the UZ defect hubris space. Whenever this Z has a non-trivial phase. Okay. So in both cases, we see that the arguments that we try to get to Lifshitz-Mattis anomalies are killed by the fact that this operator is non-invariable. So this is sort of a summary of the status. So we can try to argue the Lifshitz-Mattis anomalies from using both translation defect and UZ and a symmetry defect for ZG. But then in both cases, we can derive a Lifshitz-Mattis anomalies only if the dimension of the representations is one-dimensional, and in that case, the symmetry operators is invertible. And once the symmetry operators becomes non-invertibles, then it opens up the possibilities for the symmetry operator to annihilate the ground states in the defect hubris space. And as a result, the SPD can exist because of this loophole. So let me sort of summarize what is the final stories. So if we put everything together, then this means that there's a non-trivial Lifshitz-Mattis anomalies between the center symmetry and the Rep-G symmetry if the phase, this phase associated with the center element Z and gamma is non-trivial for every one-dimensional ERAPS. Okay, if it's a one-dimensional ERAPS, then we can basically run the same argument as this line to derive a Lifshitz-Mattis anomaly. On the other hand, the Lifshitz-Mattis anomaly is absent if this phase equals to 1 for all one-dimensional ERAPS and for all center elements. So this happens in particular in the case of D8. So in that case, we find that if we evaluate the center elements in the one-dimensional ERAPS, it's all just give you identities. On the other hand, if we evaluate it in the two-dimensional ERAPS, it gives you a -1. But this -1 can be killed using the loophole. So that's why when we take the group to be D8, the Lifshitz-Mattis anomaly is absent. So, but this is not the end of stories, because if I stop here, this just tells you that this projective symmetries are completely useless and there's nothing we can learn from that. But the twist is that there could still be interesting consequences from this projective symmetries, even if there's no anomalies. So what are consequences that we can derive? So one consequences we can derive is that we can show that the product states is forbidden to be a symmetric ground state. So let me try to prove it again by contradictions. So let us assume that the symmetric ground state is a product state. So if the symmetric ground state is a product state, then it has to respect translation symmetries. So that means that the symmetry that means that the ground states can be decomposed into products of wave functions, identical wave functions at every local Hilbert space. Then if we demand that this state is also symmetric with respect to the center symmetries, then notice that the center symmetries is given by product of SAM operators at every site. And because the ground state is assumed to be some product state, so that means that the basic unit, if we act the basic building blocks of the symmetry operators, which is given by XZ, then this XZ will act on the ground state and leave it invariant with the phase. And that phase, here's the typo, that phase has to be exponential I theta Z. Okay, so this so the fact that this ground state is a product state and commutes with translations tells us that this ground state also is symmetric with respect to just the local symmetry operators. Then now if we demand that this ground state is symmetric with respect to the RevG symmetries, then that means that this ground state has to be eigenstate of this RevG symmetries. And this eigenvalue in general is given by some non-trivial lambda gamma. But importantly, we can always pick L such that this eigenvalue is just given by d gamma. So there are several ways to prove it. So let me give you a sort of a very down-to-earth proof in this particular case. So in that case, in this particular case, we know that our ground states is some product states. And we can just decompose the wave functions at a local, at a site into sum over all the possible bases in this G qubits. So they are spanned by this states labeled by G. And now if we add this R gamma on the states, then this will read off, this will give you the characters of these gammas. Because remember, it's taking trace over the representations of G. So in particular, if we expand this states into many bases, then one of expand this expansions, then we'll obtain a state that is basically given by just product of G at every site. So if we evaluate this R gamma on that states, then we basically just get the characters of G to the power L. And because this state is the eigenstate, so that means that the eigenvalues are forced to be basically these characters of G to the power L. But G to the power L can just becomes 1 if we take L. So if we pick a L that is divisible by the cardinality of the group. So every group elements multiplied by the group cardinalities always give you identity operators. And as a result, if we pick that particular L, then the eigenvalues will be given by the dimensions of the representations. So this concludes the proof of this statement. But there's also this also agree with the expectations if the theory flow to a topological quantum field theories. So if the theory flow to a topological quantum field theories, then the ground states in the ordinary Hilbert space without any defect inserted, if we act the symmetry operators on that, it should just give you the dimensions of the representations, which are also known as the quantum dimensions of the non-invertible symmetry operators. Okay, so the first proof uses the explicit Hilbert space that we're working on, and the second proof is basically just uses general properties about topological field theories. So now, if we accept this fact that there exists R gamma, there exists an L, a system size L, such that when R gamma acts on the states, give us the dimensions of the representations, which is non-zero, then we can derive the contradictions from the projective algebra. So what we do is that we evaluate this R and X acting on the ground states. So if we evaluate that, we will first read off the phase from here, and then we'll also read off the eigenvalues from here, which is non-zero. If we pick L to be L that is given by a domain that satisfy these conditions. On the other hand, we can also commute them using the projective algebras, using the local projectivities. If we commute them, then we get an additional phase. And so we see that these two calculations don't agree with each other. So that means that there must be something wrong with our assumptions. And this tells us that we are making the wrong assumption, that the symmetric ground states cannot be a product states. So if the symmetric ground state cannot be a product states, then this actually tells us that the symmetric ground states must be entangled. So this is an example of symmetry enforced entanglement. So in this case, even though the projective non-invertible symmetry doesn't have any anomalies, it can still imply a non-trivial entanglement in a symmetric ground state. So on top of that, there's another theorems one can derive. That is, if the theory, this is a type of theorem called SPT-RSM theorems. So this is a theorem saying that what happens if the theory flow to SPT phases. So if the theory flow to SPT phases, we can show that this SPT phases must have non-trivial response. So the way to show that is, again, using the fact that there must exist some L such that when we act the non-invertible symmetry operators on the ground state, it just gives you the quantum dimensions or the dimension of the representations, which is non-zero. So this is what happens at this particular system size L. However, if this theory is described by SPT phases, then the projective algebras will demand that when the non-invertible symmetry operators has to annihilate the ground states, if the system size L satisfied give you a phase that is non-zero. So this is what we have proven before. So this tells us that if we compare this with this, so we see that they carry different eigenvalues. So that tells us that the translation defects must carry some non-trivial charges under the non-invertible symmetries. So similarly, if we consider if the theory flow to SPT phases, if we consider the UZ defect Hilbert space, then the ground states of that defect Hilbert space is again annihilated by the non-invertible symmetry operators whenever this phase is non-trivial. So this tells us that the UZ defects actually carry non-trivial charges under the Rep-G symmetries. So this is again different from the charges that we see in the ground state subspace. So the fact that this translation symmetries and the center defect, translation symmetry defect and the center symmetry defects carry non-trivial charges under the Rep-G symmetries tells us that this SPT phases have non-trivial response to the non-invertible symmetries, the ZG symmetries, and translation symmetries. So this is a type of SPT-RSM theorems one can prove. So let me just conclude with the following diagrams. So the questions now we should be asking is not about whether there's anomaly or no anomalies. So questions now we want to answer is that whether there's some usefulness, there's some constraints or no constraints from this projective non-invertible symmetries. And it turns out that whether there's a useful constraints or not depends on the precise group. And then we can follow the following flow charts to see whether there's non-trivial constraints one can derive from this projective non-invertible symmetries. So in particular, well, we need the center to be non-trivial to make some non-trivial dynamical statements. Otherwise, we don't even have the projective algebra to solve it. And when the center group is part of the commutator subgroup, then that means that there are no one-dimensional irreps that the center would act non-trivially on. So in that case, we cannot derive a Lipschitz Mattis anomalies, and at most we can derive some kind of SPT-RSM constraints or symmetry enforced entanglement. Otherwise, we can derive a Lipschitz Mattis anomalies. So let me just conclude. So in this talk, we have discussed the consequences of projective non-invertible symmetries. And unlike unitary symmetries, projective non-invertible symmetry do not always lead to Lipschitz Mattis anomalies. And in particular, that means that they can allow SPT phases to exist. And so even though there's no anomalies, there can still be a non-trivial SPT LSM theorems that implies that there are non-trivial entanglements in the ground state. So I think the talk is best summarized by this flowchart, by this plot, that all of the 1 plus 1D IR possibilities are organized here, and then we can divide them into 3 categories. One is long-range entangled, short-range entangled, and no entanglement. No entanglement just corresponds to product states. So if we have a projective unitary symmetries, which means that there's a non-trivial Toph anomalies, then product states and gap SPTs are excluded. So we're only left with long-range entangled states. On the other hand, if we have a projective non-invertible symmetries, we get a weaker constraint. And this will allow us to exclude the product states, but still leave us open with the possibility of a short-range entangled states and long-range entangled states. So that concludes my talk. Thanks.
Thank you. So do we have questions? Yes?
Hi, Tat. I wanted to understand whether your argument for symmetry and forced entanglement, does it show that the ground state can't be a product state just for this L equals L star, or does it show that it can't be a product state for any system size?
Good. Yeah, I guess that's John, right?
Yeah, hi.
Yes. So it shows that the theory cannot be in SPT phases. So I think that's a more accurate statement. The theory cannot be SPT phases. And an important result is that if the theory is in SPT phases, then it must have a unique gap ground state without a symmetry defect inserted. But now, if I insert symmetry defects, then the ground state degeneracy with the symmetry defect inserted is given by the quantum dimensions of that symmetry defect. So for example, now if I start with L star, well, which is the case when, sorry, I think I'm not sharing my screen anymore. So let me just say in words. So if I start with L star, then in that case, we know that the symmetry acts on the ground states as the quantum dimensions or dimension of the representations. So if we now change L from L star to L star plus 1, for example, then we're basically inserting a translation symmetry defect. But then by assuming that the state is a weak SPTs, then we know that the state has, if we enlarge the system size from L to L plus 1, then the ground state still has to remain one-dimensional because the translation defects just have quantum dimension 1. Yeah.
I see.
Does it answer the questions, or
but it
more
may not be
convoluted?
a product. Sorry, it may be. In principle, it could be a product state.
In principle, it could. Let me see. Sorry. Actually, I'm now confused myself now. Sorry. Let me see what I'm. Oh, I think what we have proven was I think what we have proven is when L equals to L star, the theory cannot be in product states. Right. Yeah, when L equals to L star, the theory cannot be in product states. Right. So ground states cannot always in product states. I think that's what we prove.
Okay, one more question, please.
Yeah. Hey, Tat. This is Guy.
Hi.
Very nice
Guy.
talk. Thank you. I'm just a little bit confused about your table, like this SPTs and these product states, because in your very first example, about this trivial paramagnet if you tune the sign of the Hamiltonian to be plus or minus 1. Like in the end, the conclusion is that they correspond to to different weak SPTs. Is that right?
Yeah.
But they all are product states, right?
They are all products. They are all product states. Yeah. Yes. Oh, sorry. So, but they are so SPTs are short-range entangled states. So those are SPTs. So they are product states, and that's consistent with short-range entanglement.
I see. But then, do you expect to see anything like, I don't know, interesting at the boundary if you just cut open your chain? Or
that's a very good question. Yeah, because this is weak SPTs, so it's protected by translation. But when you cut the chain opens, then you break translation symmetries. So in that case, I don't think you see anything interesting.
I see.
So it's a bit different from the usual SPTs. Yeah, but there's still not trivial response. Yeah.
Okay. Awesome. Thank you.
Yeah. Thanks.
Can I ask it? Yeah. Hi, Hota. Nice talk. I wanted to ask, just this is more background information part of the talk. Is having a Tooth anomaly the same as having an LSM, like in the simplest cases? Or does it, before you go to Rep G, or is it additional structure that you need to get LSM?
Oh, okay. So I guess that's Leo, right? Yeah. So I think one can interpret LSM as anomalies between internal symmetries and translations. Yeah, but to get something like LSMs, we need to project the symmetries. So that's one way to get LSM.
I see.
Yeah.
But so having a tooth anomaly is not sufficient. You also need to have an anomaly between some spatial symmetry and internal symmetry.
Okay. Now it's what you're asking. Yeah. So no. So you can have internal symmetries even on spin chains that has atoll anomalies. There's no problem. But I just choose to talk about this Lipschitz-Mattis LSM anomalies because it's more naturally realized. So in this case, the symmetries are on-site symmetries. And if you have on-site symmetries, meaning that the symmetry is just given by product of same symmetry operators at every site, then that symmetries cannot have internal anomalies. It cannot have anomaly itself.
Oh, I see.
But it can have anomaly with translations because translation is not on-site. So that's, yeah.
Okay, thank you.
Yeah, thanks.
Okay, no more questions. Okay, we thank again Hotat. Thank you very much. Very nice talk. Thank you.
Thanks.